So now we're in position to put it all together and find the nuclear reaction rate. Had the nuclear reaction rate here, which depended on the quantity gamma, which is a nuclear reaction rate per volume. That depends on the average of sigma times V. Sigma is a cross-section augmented by tunneling, and V is the velocity. We found now the expression of the augmented per volume. We had the classical cross-section, which is the inverse of the energy, and the augmenting factor by quantum tunneling is proportional to the exponential of minus 1 over the square root of the energy. We can substitute the proportionality by inequality in the cross-section by defining a quantity S. That would be the end of the story, except that the experiments show that S is not a constant, but it's a slope, that means a weakly dependent function of the energy. So in fact, this S here is still a function of the energy. Now, if we substitute this cross-section into the expression for the average sigma V, then we have this integral here. The main thing to realize is that this is the product of two exponentials. This is a convolution. You have the Maxwell-Boltzmann that is decreasing with energy, and the second is the quantum tunneling probability factor. It's called the Gamow probability factor because George Gamow was the first one to calculate it. And this increases with energy. Let's call it Gamow probability. When the product of these two is maximum, you have the Gamow peak. So this is the Gamow peak, is the product of these two exponentials. You have here the Maxwell-Boltzmann, so that's the exponential minus e over kt. As you see, it decreases with energy. As you go to higher and higher energies, it becomes smaller and smaller. If you relied only on this term to achieve the cross-sections needed for overcoming the potential and achieving nuclear fusion, this would never get there. As you see here, it already goes to very small values at 10 keV. It would not work. But you have then the probability of quantum tunneling, which goes as the exponential of minus b over the square root of the energy. So this term increases with the energy. When you multiply both, then you have the black curve, which then gives you the probability of reaction, which has a maximum at around 5 keV, which is about the temperature in the core of the sun. So as you saw that there is a peak where this is maximized. So instead of doing this integral here for all energies, let's just substitute it at the energy of the Gamow peak. Let's call E naught the energy of the Gamow peak. So we can replace also the SC by SC0, remove it from the integral. And then what we have is a constant C that is absorbing all the other terms plus SC naught now times an integral from 0 to infinity of an exponential, let's call GE, which has both the Maxwell-Boltzmann and the Gamow peak, where GE is the Maxwell-Boltzmann term plus the Gamow peak term. And the Gamow peak is found by requiring that this function goes to 0, where the minimum of that is. So that gives you a peak at half of b kt to the power of 2/3, which then gives you g e naught equal to minus 3 e naught over kt. So substituting that into the expression for the average of sigma v, we find sigma v is equal to s of e naught temperature to the power 2/3 and the exponential of minus 3, and substitute what b is e to the 4 pi squared 2k Boltzmann h bar squared times the mass of the electron z1 squared z2 squared over the temperature to the power of 1/3. So we can finally plug this into gamma to find epsilon. Epsilon rho, which is gamma delta E, is n1 and 2 times the average of sigma v times delta E. And since you already found sigma v, now we can also define the concentration as a mass fraction of nuclei. So X is a concentration of a reactant. So define that the number density is equal to the density times the concentration over the atomic mass unit. So if you group and substitute for the concentrations, you find then the expression for the nuclear burning rate. Now you can substitute this S times delta E over mH squared by a constant called C, and then I have the final form of the nuclear reaction rate. You can also call all of these constants here C2, and this simplifies a bit. So we finally found an expression for the nuclear burning rate. We see that the nuclear burning rate increases sharply with the temperature, given the exponential of -1 over the cubic root of the temperature. It tapers towards an asymptote. Also, because of the dependence of mass and charge, which goes on the constant C2, heavier nuclei and more charged nuclei are less likely to burn than lighter and less charged nuclei.